Assalamualaikum and good afternoon to respected examiners and supervisors. My name is Muhammad Firdaus Amin bin Muhammad Fauzi, and it is an honor to present my thesis entitled Samarium Adsorption by Oil Palm Trunk Hyrochar. So this work represents a culmination of my academic journey and my passion. So let's go through to the overview of the thesis, which include the introduction, literature review, problem statement, objective, methodology, result and discussion, and lastly conclusion and recommendation. So next, REEs pose a risk of creating hazardous contaminants and have played a significant influence in the growth of water contamination. Adsorption has been a popular approach due to its versatility, ease of use, and excellent consistency. Chemical modification can enhance Hydrochar's absorption capability and remove the contaminants from the wastewater. So from the past research, the comparison between the usage of various absorbents such as activated carbon, electrospun polyacrylic acid, and the magnetic nanoparticles for the REE adsorptions exhibit the following result. So for the REE removal method, besides absorption, there are couples of methods but has its limitation. Next is objective. The first one is to characterize the OPT-HC before and after the chemical modification. Next, to examine the optimum conditions for maximum high adsorption of samarium. And the last one is to determine the adsorption equilibrium and the kinetics of the adsorption of samarium on oil palm trunk. Next is methodology. For the first one is sample preparation of OPT 1.5 gram with 1 molar of phosphoric acid and samarium solution mixed with nitric acid and deionized water. For the sample characterization includes the utilization of ICP, FTIR, SAMEDX, Messier, and pH ZPC. Also range for batch adsorption test with the effect of pH, dosage, concentration, contact time. Include the statistical analysis for the adsorption kinetic, isotherm, and lastly, adsorption and desorption. Next is results and discussions. The OPT spectrums exhibit a distinct peaks at C308.28, typically ascribed to the stretching vibration of OH groups, particularly from the hydroxyl and carboxyl groups, as well as intermolecular bonded aliphatic hydroxyl groups from the cellulose. So the extensive peak between 2500 and 3400 indicates the existence of the carboxylic acid group, specifically derived from the phosphoric acids. The peak at 1608.33 corresponds to the CC bonds in the aromatics ring, cellulose and lignin. The bands ranging from the 3040 to 3600 show the alterations that are most likely caused by the complexations of samarium ions with free hydroxyl group, specifically from the OH group. So next is SEM. So the sample OPT featured uneven morphologies, high particle size, and smooth surface. The PAOPT has the groove-like orientation and serves somewhat rough surface and showed many pores. So the PAOPT has a stream-like surface and less dirt, more uneven after the samarium adsorption. The elements carbon, oxygen, and silica are the ones that predominate in each of the three spectra under the considerations of the EDX spectra. So based on the information presented in the table 1, it is possible to see the traces of potassium, magnesium, and calcium in the raw OPT. Following the alterations with the adding of phosphoric acids, there was not a single trace of potassium, magnesium, or calcium found. It was effectively the samarium attached to the surface of PAOPT, as evidenced by the recording of a new peak of samarium following the adsorptions of the samarium by the OPT. The PaOPT exhibits a positive charge and a lower pH than the pH-ZPC due to the attachment of extra protons to the surface functional group, thereby protonating them. This phenomenon facilitates the adsorption of anionic species and vice versa. The acquired result for the pH-ZPC is 4.16. In acidic conditions, especially low pH, on the other hand, a lot of hydrogen ions compete with the cations for the adsorption sites on the PaOPT, which make it harder for the Samarium to stick there. So at the pH 6, an abundance of hydroxide ions diminish the positive charge of PaOPT, resulting in robust interactions between the adsorbent and the adsorbate due to their opposing charges, allowing for the maximum adsorption rate of Samarium, which is 76%. The increase in the percentage removal is due to the increased availability of surface area, which increased the number of the active sites available for the metal ion binding, as the amount of dosage is increasing and is associated with a larger availability of unsaturated sites for the Samarium adsorption, which results in a decrease in the adsorption capacity. It can be seen in the figure states that the adsorption was strong after 20 minutes of contact with the PaOPT at the concentrations of 5 and 10 mg per liter of solution of Samarium solutions. The results also showed that there was fast adsorption at the outset and then a slow increase leading to the equilibrium adsorption. The opposite was true. Slow adsorption occurred as a consequence of fewer PaOPT active sites. Nevertheless, the complexation methods exhibit slower kinetics compared to the ion exchange and the hydrogen bonding reaction mechanisms. Furthermore, the estimated QE values of the second-order model are more closely aligned with the experimental values for all the starting Samarium concentrations at the mean. Therefore, it may be stated that the pseudo second-order model is more appropriate for elucidating the adsorption kinetics. By asserting that an increased concentration of Samarium provides a driving force to overcome the mass transfer barrier in the aqueous phase and the solid material surface, the elevated correlation values indicate that the Lamoille model effectively characterizes the adsorption process of Samarium, suggesting that the adsorption is likely monolayer on the homogeneous PaOPT surface. The Lamoille model demonstrated higher correlation values compared to the Freundlich model. The Lamoille model also showed that it had the maximum capacity QM, which very close to the equilibrium adsorption data. The percentage of desorption that occurs in a neutral medium with distilled water and in an acidic medium with a solution of 0.1 molar hydrochloric acid. Also, the fact that only a small amount of PaOPT was lost when 0.1 molar HCl was used compared with other two HCl concentrations, 0.01 molar and 0.05 molar, exhibit the following desorption percentage, and also it showed that the 0.1 molar hydrochloric acid had an electrostatic attraction to the PaOPT. So in conclusion, the adsorption capacity of PaOPT for Samarium enhanced with the increasing solution pH, contact duration, dosage, and concentrations. The data align effectively with the experimental equilibrium data by the Lamoille monolayer with type 4 isotopes. The experimental findings conform and more way to the pseudo second-order kinetic model. So for the recommendation, the first one is change the parameter of the test, which include the concentration of phosphoric acid used in the preparation of PaOPT. whether in a greater or lower amount. Also, the contact time, whether for the longer use and shorter use, and activation temperature for the thermodynamic studies. So for the next recommendation, the treatment should be held in the larger scale system to test the performance of the modified oil pump trons such as continuous flow columns or feeds bed to ensure the practicality.